Hi there and welcome back again. More news regarding the evaluation of predicates in relational database systems, and it's time to switch from PostgreSQL to MonetDB at this time. We will of course expect an interesting mix of stuff that we've already learned about predicate evaluation and the column-based or vector-based evaluation mode for expressions that is so typical for MonetDB, and we will not be disappointed. Let's see how expression or predicate evaluation rather happens inside MonetDB. So there we are. Time to switch gears again and switch over to the run-based MonetDB. All right. Okay, so this would be the version of query Q7 that we are using to investigate the internals of MonetDB. You see it's the scan query over the ternary table, and of course the predicate is in focus right now. Okay, let's see. We know that MonetDB can evaluate scalar expressions. Scalar expressions like this one, for example. Of course, this will be possible. And of course, this one. No problem about that. There's a Boolean return value to be expected, but that's about it. What we also need would be a means to combine the result of these two of these Boolean expressions that have been evaluated by a Boolean connective. So we need some means to implement these Boolean connectives here. And once we have the outcome of the Boolean filter predicate available, we would have to apply that to the output columns that are generated by MonetDB. And you know that the presence of a particular row of a but in the output is typically implemented in terms of visibility vectors or visibility buts that are applied using algebra projection to regular buts. And we will see that this idea also comes into play when it's time to evaluate regular predicates. Okay, all of this is in the mix now. So let's first switch over to MonetDB here. Here is MonetDB running, currently in the SQL mode. Because we are talking SQL currently, I have created the table already. I've also populated the table with the 1000 ternary rows that you already know. But what I want to do here is to actually evaluate the probe query Q7. You see that I've decided to use a Boolean disjunction here. But much of what we say could also be applied to Boolean conjunction using AND. And I actually invite you to just replay everything that you see here in this video by switching from disjunction to conjunction, and then test whether you have actually understood what happens behind the curtains when MonetDB evaluates predicates. Okay, so for the first step, let's just let the system explain what the plan would look like, the mel program would look like that is used to evaluate this query. Okay, so the plan has been output. Let's scroll through the stuff here. Lots of prelude things and stuff that's being set up. Oh, data flow, a mention of data flow. Do you recall the optimized evaluation of predicates, of expressions? The potential parallelism that hides in there. We will not look into this, but it appears to be a factor here. All right. Now let's see. So what we will see here, we have a closer look on the slide in a minute. We see well-known stuff like the access to the visibility information of table ternary and the access to individual columns. We also see expression evaluation, so computation, the application of the modulo operator with a right-hand argument 2, a literal 2. We also see some selection and comparison going on. I think that's to be expected. More column accesses, more selections that are going on, and then something new here, this merge canned function. All right, this appears to be something that is really related to the evaluation of predicates. And then some projection is going on to prepare the final result. As I told you, the outcome of the of the selection will be applied to the resulting columns A and B in our case, just as we are applying visibility information. So the same ideas come into play here. The outcome of predicates are being applied to regular buts by projection operators, and we see two of them here at the bottom of this plan, and we will come back to this when we look at the details. All right, so this is what happens in the system itself. Let's switch back to the slide set. All right, so this is the excerpt, the relevant excerpt of the mul program that you've just seen in the editor. Okay, we are evaluating this particular query. It's the variant of Q7 using the disjunction here. All right, so let's go through this step by step. Much of this is known already. So for example, the three first assignments here, they just access the visibility information for the ternary table. They then read the A column and apply the visibility information to the 8 column. All right, so in but A here, we've got, more focus. In but A here, we've got the representation of the column A. All right. When we have that, it's time to actually do some arithmetics and do the modulo operation by modulo 2. All right. So that would be the result of E1 here. Okay. But we are interested in the comparison of the outcome of this modulo operation with 0, and this is what P1 will give us. Please recall the theta select operation, which is applying a predicate to the E1 but, which is the outcome of the modulo operation, and a comparison of the tail values of the E1 but with the literal 0 based on equality. All right, so this implements this particular comparison with 0 here. Nice. Okay, this would complete the evaluation of the underlined part of the predicate. Now on to the other part of the predicate here. Again, access the column C and apply the visibility information to obtain a but C that really represents the now current contents of the but C. Okay, no further computation necessary. We can immediately perform the selection and the comparison, let's say, of C with 1. This is what happens here. Okay. So now have a look at what we get as the resulting but types when these theta select operations have been applied. The first theta select gives us the but P1, and it's a but of OIDs. It's not a but of Boolean values or something. It's a but of OIDs. The same is true for P2. It's a but of OIDs. It's all the OIDs of all rows that have qualified regarding this particular predicate, this particular comparison with 1, or this particular comparison with 0. So P1 and P2 are buts of qualifying OIDs. We are interested in any OID that could either qualify regarding this predicate or this predicate. So we will use the P1 and P2 collection of qualifying OIDs and throw them into one pot. We will merge them with the merge candidate function. And this OR but, which is again a collection of OIDs, all right, a collection of OIDs, this OR but, this is the OIDs of all rows that either qualified regarding the first or the second sub-predicate. Okay, this concludes the evaluation of the predicate. We now have to apply this outcome, to apply this the filtering result. To do that, we first access the B column. The B column is needed because it's requested in the output of the query. All right, so we first apply get the values of the B column. We then apply the visibility information of the ternary table itself, just so that we get rid of any rows that might have been removed by delete commands in the meantime, and also apply the OR but, the this is more visibility information. It might be more restrictive visibility information than the ternary table itself provides. So this is a sequence, a path of projection that is being performed. We start from B0, all the B values. We apply the ternary visibility information. This is all the current B values, okay, and then apply a project regarding the OR but, which is just the B values that would qualify regarding the predicate that we've just evaluated. All right, something very similar happens to A, but if you recall, the A but has already undergone the projection regarding the visibility in the ternary table. All that's left to do with the A column is just to apply the outcome of the predicate, the OR but. Okay, so this concludes the evaluation of the entire query. These two buts, the B res and the A res but, a string but and an integer but, these are exactly the two buts that we need to represent the final result of this selection query. Okay. So I want to highlight this idea of using buts of OIDs to represent the outcome of the subpredicates, but also the outcome of the entire disjunction. This but of OID here, as you can see. This is clarified on the next slide. Okay, so this is a peek into the but state, intermediate buts that will be generated when we evaluate this disjunctive predicate. If you recall, the left-hand side of the predicate was talking about the modulo operation applied to all of the A values. And if you look at the outcome of the modulo operation on the A values, what you will see is a but like this. A but like this, in which some of the values have a residual value of 1 and some of 0. Okay, so that would be the outcome of the modulus 2 operation on all the A values. Okay, we would then compare the outcome, the tails here, the tail values in this particular but with 0. Okay, that's the task of the theta select. Okay, so we would feed this into the theta select. We would compare the tail values with 0. The outcome of the theta select is not a vector of booleans. It's a vector of those rows that could qualify regarding this predicate. The comparison with 0 is satisfied for the but with OID 1 and the but with OID 3, and both of them are indeed found in the result of the theta select. What we have here is a so-called selection vector, a vector of OIDs whose only purpose is to represent the outcome of a selection. Okay, all the qualifying OIDs have been collected here. On the other side of the evaluation, the same thing happened. So we would just access the C column values and would just access the but of the C values. You see I've a small excerpt here, and would then apply the comparison of the C values with 1. Okay, you see this less than comparison that is being applied. Okay, so all the values, all the tail values that are indeed less than 1, they would qualify. And indeed, the outcome of this theta select again is a selection vector, a collection of OIDs, the 0 and the 1 OID here, 0 and 1. These two OIDs, indeed, they qualify regarding the comparison with 1. Okay, right. Now on to the disjunction. The disjunction would be okay with any of these qualifying rows. Any of these qualifying rows would be okay regarding the disjunction. Any row that qualifies on the left or the right path here would be in the result of the disjunction. This is the task of the merge candidate mul operation, which would read these two selection vectors and produce a merge selection vector in which all the qualifying OIDs are being collected. Of course, the OID 0 is only occurring once here. All right, so there is some duplicate elimination going on. This is really a merge operation that has been performed. This would be the outcome, the final outcome of our disjunction. Okay. So just to recap and just to summarize, the semantics of selection of filters are actually implemented in terms of candidate lists or selection vectors. Both are synonyms in this context. And such selection vectors are just butts of tail type OID, in which an entry I signals that indeed this particular row with this OID has been able to qualify regarding the predicate that is currently under evaluation. Okay, once we have this selection vector, we can just use the regular algebra projection operation to apply it to any other column in our butt. All rows that are not present in the selection vector will be projected away and will be removed. They did not qualify regarding the predicate and are to be removed. What we get out of this is a subset of the rows of the col butt, all of those rows that could qualify. Boolean connectives are simply implemented in terms of the merge can't function that we've just seen, which throws butts of OIDs into one pot, performs duplicate elimination, and leaves us with a concatenated list of OIDs, of all those OIDs that either occurred in the left or the right input, or in the case of the relation of a disjunction, we would just work with algebra projection path, a particular version of algebra projection that can apply more than one projection in sequence. We would start with this input butt here and then apply the results of the first selection vector, then apply the projection regarding the second selection vector, only those rows that could qualify regarding this and this selection vector will be in the final result of algebra projection path. This is the semantics of conjunction, of an AND filter. Okay, and the obvious implementation of algebra projection path is shown here on the bottom of the slide. This would be just a rewrite in terms of algebra projection, but as you can imagine, there is a particular efficient implementation of algebra projection paths directly inside MonetDB that avoids the construction of this intermediate result of this inner algebra projection here. And indeed, the projection path may be of arbitrary length. Many such selection vectors may be applied to one input here. Okay, so let's switch over again. Let's switch over again to the MonetDB side of things and then have a closer look at what really happens here. Okay, so this would be the probe query in question. Let's trace what really happens here on the level of mul. So let's leave the SQL console and instead open a console that can talk mul. Okay, no, this is a SQL console again. Go away. The mul console is what we need. There you go. All right. Okay, so what I'm doing here is simply replaying the plan that we have seen output by the explain before. Let's just do that. Let's initialize the SQL subsystem. All right. And then retrieve the visibility information for the ternary butt, the A column butt, and apply the visibility information on that. Okay, so this would be all the currently visible A values. I think there should be 1000 of these. Let's see. Okay, so all these 1000 values listed. This is the last OID, 1000 values indeed. All right, now it's time to do some arithmetics, the modulus by 2 operation. Okay, simply done. We have done that before. This would be the operation to perform. And now let's see what we have here. The outcome of the modulus operation is, of course, the expected alternation of zeros and ones here, because we had an ascending A column. Okay, so the arithmetics have been done. Now it's time to perform the comparison. The comparison of this outcome with 0. Let's just check The 0 occurs with all the odd OIDs here. Just to check that, with all the odd IDs, we see the zeros. Okay, so now let's do that. Let's perform the comparison with zeros here, the equality comparison. Okay, what we will get is a selection vector P1, but of OIDs, of qualifying OIDs. We expect only odd OIDs to qualify in this case. So perform the selection vector. All right, and then let's check what we indeed got here. Yes, so we got 500 rows that qualified. Every second row of the 1000 rows qualified, and indeed only those with odd OIDs did qualify as expected. Half of the selection of the filter evaluation done. All right, now it's time to look at the C, but apply the visibility information. Got that. All right, now the comparison with 1. So all those C values that are indeed less than 1. The outcome will be a selection vector. Let's already print that. Okay, not too many values qualified, actually. Only 9 values qualified at the beginning of the table. If you recall, the C column contains logarithm values, which also are ascending. So once we pass this threshold of 1, no further row will be able to qualify here. So this is the matches that we found. Only 9 matches. Okay. You have seen that we have used this algebra theta select to compare the values, the tail values in particular, but with the literal regarding a particular relation comparison operator. Okay, there's other forms of selection implemented inside MonetDB, and this is just a brief interlude, just to show you, give you a flavor of what other selection operations are available in MonetDB and in Mal. So, for example, there is a version of range selection available in MonetDB, where you would apply the algebra select operator to a particular column and then check whether the values in the tail values in that but lie between the low and high values that you specify here in the algebra select operation. All right, this can be configured to mean strictly less than or less or equal than the upper and the lower bounds of the range, but these are details that are not so interesting here. All right, so this would also be a selection operation, and as such we expect it to return OIDs, a selection vector, and that's indeed the case. So let's do that. On the C column that we have already handy, let's apply a different selection, a selection that checks whether the C value lies between 2 and 2.1. 2, the inclusive, 2.1, the upper limit, exclusive in this particular range. This is guarded by these Boolean flags. So let's do that. Okay, so range selection performed. Let's see the selection vector here. Okay, so some rows qualified, indeed 26 rows qualified, it appears. Okay, somewhere from the middle of the range of the ternary table, to see that we've really selected the qualifying C values. We could now use that selection vector, here we are, and apply it using algebra projection on the current C column. What we will get is the qualifying C values. Okay, let's do that. Applied, and then print the C values that have qualified. And indeed, it appears to be the C values in the range between 2 inclusive and 2.1 exclusive. All right, so that would be one example of another selection operation that's present in Mal. Okay, but now back to the evaluation of our probe query. All that's left to do is actually use the P1 and P2 selection vectors and throw them into one pot, because we are evaluating a disjunctive query. Okay, and that's the task of the merge can't function. So let's do that. Throw them into one pot. Okay, and then print the final result. This should be a selection vector of at least 500 entries. There might be some more entries that are contributed by the P2 side. P1 alone had 500 entries already. Let's see, 505 entries. So 505 entries, all in all 505 rows have been able to qualify regarding our disjunctive predicate. So now all that's left to do is to construct the result. And as I told you, this means the construction of the A and B result columns. So we would access the B values, the current B values, and then use these B values, the raw B values, and apply the visibility information of the ternary table itself, as well as the selection vector that has been found in our predicate evaluation. Okay, so that would be the resulting B values. Now the resulting A values, as I told you, A has already undergone projection regarding the visibility of the ternary table. Just the result of this filtering has to be applied here. Let's do that. And then finally, let's print the result. A res and B res, these two buts contain the result. And there we go, 500 rows qualified. These are only even. These are only even A values, which makes sense because we have applied this predicate that asks for even A values. Maybe there is even some odd values among these. If at the beginning of the result, probably, if the other part of the predicate, the C less than 1, was evaluated to true. Okay, some odd A values in there. Oh yeah, 9, 7 at the beginning of the table as expected. All right, as we've already seen. Yes, so that's it. That's the evaluation of predicates, complex predicates rather, in MonetDB. And we will see that index support for the evaluation of predicates is present in MonetDB, but has a way less prominent role than in PostgreSQL, and for good reason. All right, but we are not done yet with our discussion of the evaluation of selection in MonetDB. The next step of this adventure will lead us much deeper into the system, directly onto the CPU. Okay. Looking forward to discuss this with you in the next video. See you then. Bye.